Welcome back. Functional Analysis FAV 02 of 02 by Prof.Dr.A.G. Srinivasan. A compact subset of a metric space is closed as well as bounded. What about the converse? Let's take the converse part. The converse need not be true. What is the converse? Suppose X is a metric space which is closed and bounded, it need not be compact. If X is closed and bounded, it need not be compact in general. Can be compact for some examples, but in general, for a metric space, if it is closed and bounded, it is not compact, which I'm going to show an example after a few minutes in 4C. This is my 4. A is the observation, the converse need not be true. In 4C, you will see the example. Now, before I do that example, let me take a very, very classical theorem which I'm going to prove immediately after this. What is that? If X is finite dimensional, X is compact if and only if X is both closed and bounded. So this lemma says a compact subset of M of a metric space is always closed and bounded. And further, we are going to show by means of an example, the converse need not be true, where the converse is if it is closed and bounded, it need not be compact. If it is closed and bounded, it need not be compact. But in a finite dimensional non-linear space, compact implies closed and bounded. Closed and bounded implies it's compact. This is what you're going to show in 5. We will see that after a few minutes. What is that? So 4A says the converse is not true. 4B says in a finite dimensional vector space, compactness implies both closed and bounded. We already saw in the last video, in a finite dimensional vector space, it is always closed. Finite dimensional vector space, non-linear space, it is always complete. Finite dimensional non-linear space is always Banach. So all these things we have seen in the last class. And even we proved in the last class, in a finite dimensional non-linear space, any two norms are equivalent. Any two norms are equivalent. And we are going to have one more feather to this discussion, that in a finite dimensional vector space, compactness implies both closed and bounded. Closed and bounded implies compactness. We'll prove it after some time. Now, we are going to the example I'm going to show you in 1 minute. If it is closed and bounded, it is not compact. It's very obvious. I will now take this L2 space and take En is equal to delta Nj. Well, delta Nj is equal to 1 is equal to 0. If you don't remember what I said, let us recall what is that E1. What is E1? Let me take it now. So what is my E1? My E1 is going to be 1, 0, 0, etc. E2 is going to be 0, 1, 0, etc. like that. So what is En? It's delta Nj. So the nth term is going to be 1. So first term is going to be 1. Second term is going to be 1. So nth term is going to be 1 and it's 0. So this En, it's a basis. It's a basis. It's a basis for L2 space. It's a basis for L2 space. But I'm not interested in L2 space as such, but only what is important for me is to tell you the En equal delta Nj. This sequence is bounded because norm of E1 is 1. So if you take this En, take the norm of E1, it's going to be square root of 1 square plus 0 square plus 0 square, etc. So norm of En is 1. So you know that simple mathematics tells you norm of En is 1, therefore it is bounded. So the bound is less than or equal to some k, but it's going to be 1. This 1 does not depend on n. So when norm E1, norm E2, all of them is equal to 1, so it's always bounded. It's always closed because it has no limit point. So recall the first unit, what we discussed was the limit points, accumulation points, M bar, enclosure, all that. So this is always closed. So for the same reason, so it is both bounded and closed, but for the same reason, it can't be compact because it is, if it is not having an accumulation point, it cannot be having a convergence of sequence. It cannot have a convergence of sequence. So it can't be compact. So what we try to show is that this L2 space is both bounded and closed, but it is not compact. That's not important for me. Which is under 5 states in a finite dimensional norm space X, any subset M of X is compact if and only if it is both open and both closed and bounded. So what we proved in the previous video is that in general, if M is compact, in general, if M is compact subset of a matrix, M is a compact subspace of a metric space XD, it is always closed and bounded. However, if M is closed and bounded, then M need not be compact. That's what we said in the previous video. Now we are going to show if it is finite dimensional, then the compactness and the closed and boundedness are equivalent. M is compact if and only if M is closed as well as bounded. Equivalently, if M is compact, then M is closed and bounded. If M is closed and bounded, M is compact. We are going to show this now. It's very easy. Now for this, we are going to use a result we proved in the last video, I think FAV 022. We proved this video in that itself. If xn to xn are linear independent set of vectors, then norm of alpha 1 x1 plus alpha 2 etc. alpha and xn is greater than or equal to c times modulus of alpha 1 plus modulus alpha 2 etc. modulus alpha n. We proved in the last video this property under linear combination. Very important property. We use many times this property in proving this. Then we talked about Bolzano-Weierstrass theorem, which you supposed to know from analysis class. Don't worry, it says every bounded infinite subset of Rn as a limit point. Every bounded infinite subset of Rn as a limit point. So every bounded set is convergent. That's what I mean, okay, in some sense. So every bounded infinite subset of Rn means R, R2, R3, etc. as a limit point. This is well known as Bolzano-Weierstrass theorem. You must have studied in your UG class or even first semester reanalysis class. So every bounded infinite subset of Rn as a limit point. Rn means real number R, or R2, R3, etc. So I'm going to use these two results to prove the main theorem. What the main theorem says? If X is finite dimensional, then M is compact if and only if M is both closed and bounded. Now proof is very immediate for the following reasons. From the previous lemma, we already had the lemma 4. Lemma 4 says, first of all, that if M is compact for any metric space, if M is compact, it is closed and bounded. So there are two parts here. First part is that if M is compact, I must show it is closed and bounded, which I already proved in 4. Now if it is finite dimensional, I would like to show if it is closed and bounded, it must be compact. If you prove that, the premise proved. Okay, so let's go to the main theorem. So we wish to prove by the previous lemma, compactness implies closed and bounded. We wish to prove that if M is subset of X such that M is both bounded and closed, then M is compact. Of course, we can prove only if X is finite dimensional. I repeat, we wish to change the color to differentiate the argument that we are going to show that we wish to prove that a subset of M which is both bounded and closed, it is compact if X is finite dimensional. This is what we are going to show in the next few lines. You see, proof is very easy. Don't worry, we'll see how the proof works. Now, what is dimension of X? N. Because X is finite dimensional, I assume the dimension of X is equal to N. And because it's finite dimensional, we can find a basis E1 to En for X. So take a sequence in M. What is Xn? Xn is sequence in M. Now for each M, Xm can be written as a linear combination of A1M E1 plus A2M E1 etc. An. There's a definition of dimension. Every element in M can be expressed as a linear combination of EIs. So Xm is equal to A1 E1 plus A2 E2 etc. An En. Because there's a M here, I put a M here as well. So Xm is equal to A1 power M E1 plus A2 power M E2 etc. An power Em. You are assuming that M is both bounded and closed. Bounded as well as closed. Okay, we are assuming that. So because of that, since M is bounded, Xm is also belongs to M and M is bounded. Therefore, this Xm is also bounded. Because we know if a sequence is bounded, every subsequence also will be bounded in any M, of course. And because M is bounded, because Xm belongs to M, Xm is bounded. What is bounded means? Norm of Xm is less than or equal to K for some K positive, and this K do not depends on M. right? For every m, xm less than or equal to m. K. So m is bounded. So this xm is going to be less than or equal to k. But what is xm? Xm is a1 power m e1 plus a2 power m e1 etc. an power m em. So if you use that here, this k is smaller, so k is greater or equal to norm xm. The norm xm is nothing but sigma j is equal to 1 to n ajm over ej, and as in this result, okay, the norm of this sum is greater or equal to c times modulus of the norm, the modulus. I'm using that result. So this is going to be greater or equal to c times sigma j is equal to 1 to n modulus aj power m. What are the aj's? Aj's are scalars, belongs to R or C. A finite vector space, a non-linear space, is a real vector space or a complex vector space. So A1, A2, etc., ANMs, all of them are real numbers or complex numbers. So AJMs are real numbers or complex numbers. Of course, by that lemma, C is also positive. So K greater or equal to C sigma J is equal to 1 to n AJ power m. Or equivalently, sigma J is equal to 1 to m modulus AJ power m is less than or equal to C by K. What is C? Positive. What is K? Positive. So C by K is also positive. That means AJ power m summation of that is less than C by K. And this C by K do not depends on both J as well as M. This does not depends on both J as well as M. That means this AJM is bounded as well, because this does not depend. The C by K is a fixed number that do not depends on J and M. So AJM is bounded. And what are AJM? AJM are elements of R or C. C is R2. R is R1, R power 1. C is R2, R power 2. So these AJs are bounded, and therefore by Boltzmann-Weierstrass theorem we just now stated, every bounded infinite subset, infinite of course is obvious, has a limit point. So therefore this sequence AJM has a limit point AJ. So this AJM has a limit point by Boltzmann-Weierstrass theorem, because every bounded sequence in Rn, in R or C, has a limit point, because Rn is R, R2, R3, etc. R2 is C, R1 is R, etc. So AJM as a limit point to as AJ. Now, this means, okay, this means that the subsequence converges to M. Now, this AJM converges to a limit AJ, and AJ as a limit exists, okay, AJ as a limit exists, and M is already closed, we already saw it. Therefore, every sequence xn has a convergent subsequence, If it is not clear, let me explain little differently. This AJ as a limit, AJM as a limit AJ. So AJM converges to AJ. So the corresponding AJM, the subsequence AJM, EJ converges, because AJM certainly converges. EJ of norm 1, because it's already bounded. So it's a subsequence also converges. That means the sequence xn as a convergent subsequence. Therefore, in that context, M is bounded. All these were possible because of the fact X is finite dimensional. If X is finite dimensional, I cannot write in this way. So we got a subsequence for the sequence XM that also converges, right? Therefore, M is compact. Now we are going to show the next. This is Professor Dr. A.G. Srinivasan. Thank you.